All right. This video is going to review what I'm going to do is review the dynamics quiz that you guys recently took, which was on AP Classroom. It was around 20 questions or so. Um, I'm going to go over each of these as best I can, um, starting with this inclined plane problem. It says block A is placed on a rough. When you say rough, of course, you have to be aware that that indicates there's friction between the block and the incline. Block A is placed on a rough surface inclined at an angle theta above the horizontal. A taut string connects block A over block B. Taut means tight. String connects the two, which hangs from a string as shown below. The masses of blocks A and B are unknown, just represented as MA and MB, respectively, means in that order. At time t equals 0, block A is sliding up the slope, indicated by the velocity vector, showing it's moving up the slope, as block B falls. And the blocks are both slowing down. Assume that the mass and friction of the pulley, assume that the pulley has negligible mass, not a lot, and that the string itself also has. All right, what's the question? If the mass of the block B is 2 kilograms, what is the gravitational force exerted on block B? So in this case, they're asking us for the weight of block B. So we know that the gravitational force, usually represented like this in magnitude, if you want to use that symbol sign, is m times g. I mean, technically speaking, we just write Fg equals mg. If you wanted to write it as a vector, usually you would write it as Fg as a vector equals m times g as a vector, meaning that the gravity force, which is down, is in the same direction as the vector that's on the other side of the equation, which is g, Earth's gravity, which is down. In magnitude, technically, you'd write it like that so that you weren't putting in negative in for g if you were wanting just the quantity, the amount of weight. They did say that the mass was 2 kilograms, and if we're using 10 as an approximation for the acceleration due to gravity on Earth, we would get an answer of 20 newtons. That puts the answer as C. All right, see the next question. Looks like a similar scenario, similar description on top. They continue to say for number 2, the two blocks, since this original block was, remember, moving upwards originally, at some point it'll hit a point where it stops and then it reverses direction, comes back down. Which of the following graphs best predicts the acceleration of block A? I don't know if predicts is, I think represented is a better word. Which of the following graphs best represents? But either way, the acceleration of this block as it moves up, stops, and then comes back down, this rough inclined surface. Assume that the positive direction points down the slope. So let's take a look at that. So there, usually, you have the choice of determining which direction is positive. So they're deciding to say that the positive direction will be down the slope and the up the slope direction will be negative. So we know that if something is moving in the upward direction, if V was originally this way and it was losing speed, which they said, I believe, right? They said it right here. It says blocks are both slowing down. So we know if a block is moving up the incline but slowing down, then the net force on that block has to be in the other direction, right? The net force was in the same direction as V, then it would accelerate and gain speed. So we know already that the net force must be down on this block, which they call block B, or sorry, block A, because that would cause it to slow down. If the net force is down, and Newton's law, F net equals ma, the net force on block A is equal to block A's mass times the acceleration of block A. And the net force and the acceleration vectors are always in the same direction. So if we already identified that the net force is down, then the acceleration for block A must also be down. Still in agreement with what we've learned previously in the kinematics unit, which is when a velocity is to the right, if it's slowing down, that means the acceleration is to the left, because the net force has to be in that same direction to cause it to slow down. So that means we've already determined that the acceleration is down, which is plus. So graphically, if we're graphing out acceleration versus time, we already know that there has to be some positive value for the acceleration, and we know it's constant because the forces are constant. The net force doesn't change as it goes up and down. The amount of downward force, which is mg sine theta on him, and the tension pulling him up, since this was, of course, connected to the pulley, these forces don't change. Those forces are fixed throughout the whole motion. Even for this guy over here, the tension pulling him up and his weight down, none of those forces change, constant. So if the net force is constant, we know the acceleration has to be constant. If the net force is increasing with time, the acceleration is increasing with time. If the net force is decreasing with time, then the acceleration is decreasing with time. When one is constant, the other is constant, which is why this has to be flat. Right? Oh, one other part to this I'm forgetting to point out. They said that there was a frictional surface here, right? Better add that to it, because they said originally said it's placed on a rough surface. So I know that the acceleration must originally be as I've described so far. Let's continue to look at our choices here. So I think we can conclude that regardless, even when this block is now moving down, if I drew another picture of it, now it's heading down. It's gaining speed as it moves in this direction, right? It speeds up as it comes down, which means the acceleration is still down because the net force is still the same value that it used to be. Doesn't matter whether it was going up or down. So we know our graph has to include accelerations that are all positive, right? So even when we throw a ball up in the air, ball goes up. Which way is the acceleration due to gravity? Down. While it rises, the acceleration due to gravity is down. At the top of its path, when it stops, the basketball stops at the top. Which direction is acceleration due to gravity? Down. As it falls, which direction is acceleration due to gravity? Down. Acceleration doesn't change unless the forces change. And since you're throwing a ball, the only force is really the force of gravity if we're talking about air resistance scenario. So that you have to keep in mind that the forces are if the forces are constant, then the accelerations are constant. If the net force, I should say, is constant, the acceleration is constant. And it's in the same direction. If it switches direction, then you'd end up with something like this. If the acceleration was up the ramp, down the ramp, which was positive, then you'd have this. And if you thought that switching direction causes the acceleration to change sign, and now as it slides down, the acceleration is actually up the ramp, which we're calling negative, and I know it's confusing, but up the ramp is now negative, then you might be thinking something like this. But it's always down the ramp, which is positive. Really what we have to work out is it a constant positive value, or is it positive and then does it decrease? And that takes even more thought. This is a hard problem, in my opinion. Think of it this way. You have mg sine theta, which is the gravity force, FGX, pulling this block down the ramp, MA, right? It's always pulling him down, mg sine theta. As he moves up the ramp, which direction is the frictional force? In the opposite direction. So the frictional force, all right, FFK for the kinetic friction force is down. How about when the block is coming down the ramp? When the block is coming down the ramp, mg sine theta is still pulling him down. That's the FGX. But now which way is the friction force? If he's moving down, the frictional force is actually, I shouldn't have drawn it. Draw it the same length as I drew it before. FGXs will be the same, but now the frictional force is the other way. Because he's moving down, the frictional force would be up. So in which case is the net force the greatest value? Like if we called down positive, let's just put some numbers here to make sense of that. Let's just say this was the number 6 newtons, and this was 3 newtons of friction force. Then what would the net force be? In this scenario, the net force would be 9 newtons because they're in the same direction. But how about when it's coming down the ramp? FGX would still be 6 newtons if that were the case. I'm just using these numbers to illustrate an idea. And the frictional force would be still 3 newtons, but in the other direction. what would the net force be now? If this is +6 and this is -3, this is a +6, this is now a -3, right? So now the net force would be only 3 newtons in the downward direction. So you end up with far more net force, extra force in a certain direction, which is when it's coasting up, and that extra net force, that net force is down the hill, down the incline, and the amount of 9 newtons in my example. So in which scenario would the acceleration be greatest? Well, whenever the net force is greatest, right? So that means you'd have a high acceleration when the net force is high, 9 newtons, and then you'd have a lower acceleration because the net force drops. If the net force drops, as soon as you switch direction from 9 newtons to 3 newtons, the acceleration drops. Stays positive, it's still down the ramp, but if it's now dropping in value, we'd have to pick B to indicate that the acceleration actually drops. Stays positive, still down, because the net force is still down the hill, but it's less due to this reversal of the frictional force. So B would be the correct answer there. I consider that a pretty difficult question. 5 kilogram, number 3, a 5 kilogram object is released from the rest on near the surface of a planet where the gravitational field is constant. Gravitational field is just, think of it as G, right? So when we think of when we think of a planet like this, G is really a vector that points inwards. It's essentially a field, like a force field that surrounds the planet, and it pulls all masses inward towards the center of the planet. Later on, we'll recognize that the G value actually gets smaller and smaller as you go further and further away. So this little vector G would get less and less and less as you got further and further away. But for now, it's sufficient to just call this concept, what we call G, of 9.8 meters per second squared, the gravitational field, the strength of the gravitational field. On the surface, when you're at a certain distance, it's constant. You'd have to go further out, like here, for it to be less of a value all the way around this circle. Or all the way out here, it would be the same value all the way around that circle, no matter where you stand all around this. So at a certain distance from the center, it's considered constant. Just trying to make sure you understood what that meant. Gravitational field is considered to be constant. Doesn't change to be 10.1 or 9.7. Everywhere on the surface, it's 9.8. The mass of the planet is unknown. After 2 seconds, the object has fallen 30 meters. Air resistance is considered negligible. What is the gravitational force exerted on the 5 kilogram object near the planet's surface? So in this case, they're asking us to solve for the gravitational force, again, almost like the first problem. And they told us that the mass of the object is 5 kilograms. We just don't know what G is. We'd end up having to work out G. They gave us enough information. They told us that something is falling some distance after dropping it. You release it from rest, it said, and it falls a distance of 30 meters. And the time that it takes for it to fall from here to here is 2 seconds. So technically, we have the position formula, right? Distance equals 1/2 AT squared. Could call it delta y if you wanted, change in vertical height. And we're solving for the acceleration here is really the acceleration due to gravity because it's falling, right? So if I solve this for G, because we need it right here, algebraically, I'd have to multiply both sides by 2. The 1/2 and the 2 would cancel. I end up with 2D equals GT squared. And then I divide by T squared, right, on both sides. And I'd end up with G equals 2D over T squared. So now I can compute G. The distance they said was 30 meters. And the time was 2 seconds. Don't forget to square it. So it looks like I get 60 divided by 4, which I know is 15 meters per second squared. So it's a planet where gravity is stronger in the amount of 15 meters per second squared. That number is G. We can now stick it up here to calculate the weight of this 5 kilogram mass when it's on this planet. 75 newtons. That would put the answer in at D. Number 4. Here's now, first time I read this through, to be honest, I actually missed that they were literally just asking me for the weight of the block. I thought maybe there was something more complicated they were asking. Here's a modified Atwood machine. Some force is pulling this to the right. It could be your hand pulling it. You're familiar with this picture at this point. It's accelerating in the upward direction at a rate of 3a, so on and so forth. And they describe all of this, but then they just ask, what is the weight of this block? Well, if this is the mass of this block, then the weight of this block is this times g, mg, d. All right, number 5. Now they're showing some amusement park ride where somebody gets pulled up. I've done this before. It's fun. It's a fun ride. It pulls you up slowly, then it holds you at the top, then it waits 3, 2, 1, and drops you, and you go into free fall, and you fall straight down. And then pneumatic systems that use pressurized air to slow you down, which is why you hear the sound. You hear it slowing, and then it stops you right here. But there's a period, like this, where you're in free fall. It starts to slow you down, slow you down, slow you down, stop. Anyways, what's the question? Which of the following indicates the magnitude of the gravitational force exerted on this rider? Remember, the magnitude of the gravitational force is just his weight, mg, since he has a mass of m. Which one of these things best describes what he weighs on the way up and on the way down? Remembering that the gravitational force is just his weight. Don't let it confuse you. Does your weight change as you go up or down? Of course not. You weigh mg on the way up and you weigh mg on the way down. C. Number 6. Two identical spheres. When they say identical, it means they are identical. Identical in shape, identical in size, and identical, more importantly, in mass. Identical spheres are dropped, well, more importantly, I say, because most of the time in AP Physics 1, we're not referencing air resistance. So if it's dropped in a vacuum, the shape and size of it doesn't matter. All that matters is the mass. If there is an air resistance and you are considering the atmospheric effect of air resistance, then the shape, geometry, volume, such would come into play, but not the case in this course, generally speaking. So if we're considering dropping 2 spheres, dropped from a height of 1 meters, one on planet X and one on planet Y. We already know that 2 different planets, more than likely, very likely, definitely, I dare say definitely, have different accelerations due to gravity. They'd have to be the exact same volume and the exact same mass for them to have the same g. They'll have different accelerations due to gravity, meaning when you drop one sphere on planet X and drop the other sphere on planet Y, they both gain speed at different rates. The stronger gravity planet will cause the object to gain more speed more quickly. And the other lower gravity planet will cause it to still fall and still gain speed, but not as quickly. Maybe planet Y has an acceleration due to gravity of 5 meters per second squared, which means after 1 second, it has a speed of 5 meters per second. While on planet X, it only has an acceleration due to gravity of 3 meters per second squared, which means after 1 second, it only has a speed, falling for 1 second, it only has a speed of 3 meters per second, right? If that were the case, planet Y would have more acceleration due to gravity, and that idea that it would have more speed after falling for 1 second compared to the other one after falling for 1 second. All right, what's the question? The position of the spheres as a function of time is recorded and shown, because they were both dropped from the same height, just on different planets. Which planet exerts the greater gravitational force on the sphere? And what evidence from the graph supports this conclusion? So on which planet are we seeing a greater acceleration? Well, on planet X, it's able to fall 100 meters in a little over 6 seconds. On planet Y, it falls that same 100 meters in a little over 4 seconds. So it's gaining speed at a faster rate, causing the time that it takes to fall 100 meters to be less, right? So we must have greater gravitational force and field in planet Y. But we also have to select for what reason. For planet Y, let's look at C and D, because the area under the curve is smaller. So the area under the curve does have some applications for sure, but for a position versus time graph, the area in here is meaningless. For velocity versus time, the area under the velocity versus time graph represents displacement, while for the acceleration versus time graph, the area under the curve represents change in velocity. However, when you're looking at a position versus time graph, though the slope, or in calculus we call the derivative, the slope of a tangent line, if there's a point here and we drew a tangent line, That slope has meaning, which is instantaneous velocity for a position versus time graph. The area under the curve actually has no meaning. For that reason, I know it's out. It must be this answer, but only because I knew that. Let's just look to see what they have as a justification. Planet Y, which we knew, this one, accelerating more quickly. For what reason? Because the magnitude of the slope of the curve increases at a faster rate. Oh, good. They're referencing the slope of this curve, right? At this point, there's a slope there. That's the instantaneous velocity at 2 seconds if I drew a dot here and drew a tangent line. If I drew a dot here, then at the 4-second mark, the slope of that line, that tangent line to this 4-second mark, represents the velocity there. They're pointing out that this has a greater acceleration, this planet has a greater acceleration since the slope is increasing at a faster rate here, increasing at a slower rate here. Sounds right. So for that reason, it's D. Question 7, 2 identical blocks, block A and block B, are placed on different horizontal surfaces. Block A is initially at rest on a smooth surface, while block B is initially at rest on a rough surface. Okay, so we have 2 objects. Block B is apparently on a rough surface. I keep track of all this stuff. I'd like to draw some pictures. You might want to consider doing the same thing. The other one's on a smooth surface. They did say 2 identical blocks, so that it tells me they have the same mass. Their inertial properties are the same. It means providing a certain net force to both of them will provide the same accelerations. They'll gain speed at the same rate since their masses are the same. Their resistance to acceleration is the same. Their response to a net force is the same. So those details are there. Block A is initially at rest, all right, on the smooth surface, while block B is initially at rest, okay, on the rough surface. Okay, got that. A constant horizontal force of magnitude F naught, F sub 0, whatever you want to call it, some force, but the same force is being applied to both. It's 3 newtons of force applied here, it's 3 newtons of force applied here. And they said constant, so it's not a push and a release, it's you're pulling it, or you're continuing to pull on both of these with a constant force. That's the same in both experiments. After the force has been applied for a time delta t, who knows how long it is, nobody cares. The speeds of the blocks A and B are BA and BB. We don't know. So some amount of time later, we know that block A has a certain speed, velocity I should say, with the magnitude being the speed. And VB also has some. However, are they actually at the same position? Well, if they're at the same position some amount of time later, delta t later, then that means their speeds are the same, and I would be concluding that VA is equal to VB. And that's not even one of the choices, because they won't be at the same positions, right? Though their inertial properties are the same and they respond to net forces equally, only one of them is subject to the frictional force, which reduces the net force, right? So if the net force is, well, we know that the frictional force on him would be in the other direction. Maybe I'm drawing it like this, the sliding friction force. That means the net force on this guy is this minus this amount. Subtracting that amount off, I'm like, oh, well, that's smaller. That's a smaller net force. So this guy has a smaller net force acting on him because the frictional force is subtracting away from some that's here for the pulling force. He's got the full pulling force. That is his net force. So who would actually reach here first? He would. Why? Because the net force on him is greater than the net force on him, because he's losing some net force due to the reduction of the that's occurring due to the sliding friction effect. So if I were to draw the real picture, A would be the winner if it were a race. B would be somewhere behind. Right? They both started here at rest, as almost always the case. And this was frictional. This is what causes the difference in these distances they've traveled in the same delta t. And therefore, what can we conclude about the speed or velocity, magnitude of this guy's velocity versus the magnitude of this guy's velocity? He's going to have more speed, right? because his acceleration is greater, right? And also have pointed out that the acceleration for either of them is their net force divided by their mass. Since he has more net force, remember this picture, he has more net force on him, this guy has less. Since this guy has more net force on him, he'll have more acceleration. Since he has more acceleration, we could make the point that the final speed after delta t seconds, and I could have written this as a delta t, since he has more net force on him, as we've agreed, and he, which is block A, has more acceleration as a result of that extra net force. He's got more acceleration. And if he accelerates for the same amount of time delta t as the other guy, since he's speeding up at a greater rate, his final speed would be greater, right? Which is why he's ahead. So we can conclude that VA must be greater than VB. Now it looks like we have two choices for that, C and D. Now we got to distinguish, because now there's also a justification that's being attached. It says right here the justification. I lost my. So we have to read the justifications for this. Well, we know it had to do with friction, right? It's totally had to do with friction. The forces between the atoms in the block and the atoms in a surface oppose the motion of the block and are greater for block B. Yeah, that's friction. They're describing friction from an atomic scale, that the atoms between them cause a sliding frictional effect that opposes the motion of block B. And that effect of friction, is a greater effect for block B. And that's why we can conclude VA is greater than VB. Correct, so D. D should be the answer. Number 8. Which of the following experiments could be used to determine the inertial mass of a block? Now, what do we mean by inertial mass? Inertial mass you can think of as the resistance to a net force. So technically you can imagine, because remember, gravity pulls downward. So if we want to know the gravitational mass of something different than the inertial mass they're mentioning here, we'd want to do some experiment with something that is moving along the direction of gravity, either up or down. If they're asking us about the inertial mass in a gravity field, then you'd want to move something perpendicular to gravity, since this, what we call the independence of motion. Horizontal things aren't affected by vertical things, and vertical things aren't affected by horizontal things. So by moving sideways, we're more or less getting away from the effect of gravity. And therefore, if we apply a net force to it, we know that the acceleration that we see as this thing accelerates along, right? This would be accelerating, greater distance moved each second. This acceleration would be equal to the net force applied in this direction, divided by its inertial mass. This is the inertial mass, because it's giving us, this is M, by the way, M for mass, and then this is the word inertial. This is the inertial mass because this is giving us a way of seeing how it resists being accelerated due to its net force, due to the net force being applied to it, I should say. All right, so you'd want to be looking for some sort of experiment in this question that they've asked, which is, which of the following experiments could be used to determine the inertial mass of a block? Definitely want something that's involving something that moves sideways. See, let's read them. Place the block on a rough horizontal surface. Well, rough is already not great, because if this net force has to be broken into a forward force, which is the applied force, minus some kinetic friction force, because the free body diagram for this block that's moving has some forward force applied to it, some backwards kinetic friction force. Of course, there's these vertical ones about along this vertical axis as well. But horizontally speaking, if you're doing it on a rough surface, then because there's friction backwards, now this becomes more complicated. If you're trying to determine the inertial mass of this, it's better just to be on a smooth surface so that this is an easy thing to measure, right? And also because friction is actually affected by the gravitational mass, right? Because remember, friction on an atomic scale, due to the roughness and textural, textural jaggedness, if you want to call it that. Friction comes from that idea and of them being rough. And how tight, the frictional effect in here depends on the normal force, right? Depends on how tight it is inside here. But the normal force, which is a measure of how tight it is in here, affects the frictional force. The frictional force in here depends on how much pressure there is, right? Well, how much pressure there is actually affected by the weight, which is related to the gravitational mass. This is the gravitational mass. It's how much force it feels in a gravity field due to its mass. So since, again, as soon as you start talking about friction, you're automatically invoking the concept of gravitational mass into it, right? Because in fact, to even calculate the frictional force, it's the kinetic friction force coefficient times the normal force, which for this simplified problem of something just sliding to the right is mg, where that's the gravitational. That's the gravitational mass. So you wouldn't want to do an experiment that involves friction due to the effect that, or the idea that that friction includes gravitational mass, inclusive of that force. So let's look for something that maybe is not including rough. I mean, you could still probably do it, but I don't know that it would be the best way to go about, would be very accurate to determining something that's determining just the inertial mass. B, drop the block from different heights. Dropping something, that's a gravitational mass thing, right? That's moving down in the direction of gravity. We're talking about inertial mass here. C, place the block on a rough horizontal surface. We're talking roughness again. I don't like roughness. Let's see what D offers. Use a spring scale to exert a force on a block. Measure the acceleration of the block and the applied force. That's probably the simplest one I'd have to pick. All right, so they're saying they haven't talked about the surface. I'm surprised. But remember, if they don't mention friction, then the assumption is there's no friction. There's no mention of friction in D. So we're assuming this is a smooth, frictionless surface, or close to it. Have some sort of scale that you use that pulls. You've seen them in the Pivot Interactives, a little scale, and you pull it. And if you can measure that pulling force, and then do kinematics and slow motion analysis to determine the acceleration dependent upon the distance and the delta t, remembering distance equals 1/2 t squared. That gives you access, measuring these two, gives you, well, that assumes that it actually starts at this spot. If it starts here, then that's where you'd measure the distance. If it starts from this point, that gives you access to A, right? And therefore, you'd be able to measure the force, like they just said, calculate the acceleration based on these observations, and then you'd say that net force is just this. Because remember, the normal force and the weight are canceled. So when we're talking about net force, the net force, these cancel, but this is the net force. So this net force becomes the thing that you're pulling it with, and therefore you could technically solve for M. This would be measured from the spring scale. A would be measured from doing the kinematics, and that would be inertial mass. So for that reason, it would be D. Number 9. A 1,500 kilogram car traveling along a road is hit by a 0.1 kilogram rock that creates a small crack in the car's windshield. Which of the following describes the interaction between the windshield and the rock? Now you have to remember that Newton's third law truly indicates that in all cases, and I mean and in all cases, forces come in pairs. You can't have one thing feel a force without something else feeling a force. They both feel the force. If I'm feeling a force from my chair because I'm sitting in it right now, I guarantee you my chair feels that same force too, but we feel a bit opposite directions. My butt feels a force in the upwards direction from the chair, but if you were the chair, you certainly would say that you were feeling a downward force from my butt. The amount of force is equal in both cases. If I had to have a conversation with the chair, We both find that we feel the same amount of force, but again, they're in opposite direction. My force that I feel from him, the chair, is up, while the chair feels a force from me, which is down. Every action, which is what we're calling a force, causes or creates an equal in magnitude, the force, and opposite in direction, reaction. Every action has an equal and opposite reaction. That is Newton's third law in all cases. In all cases, regardless of any details. So when they try to give you these tricky questions, which is like a bug is splatted up against a windshield while a car was driving, which object felt the greater force during that collision between the bug and the windshield? Most people want to go for the bug because it's tiny and it destroyed the bug, so it must have felt more force. Isaac Newton would say, that's not right. The acceleration was huge for the bug, not because it felt more force than the car did. He'd say, my third law says that they feel the same force. The car and the bug feel the exact same force. The reason that that force killed the bug is because of its low inertia, very small mass, right? He'd say, and my second law suggests that the acceleration is inversely proportional to the mass, assuming that they both have the same net force, right? This would be F net. Same force. They both feel the same force, but in opposite directions. But the bug with a tiny, tiny mass, you put a tiny number here, going to cause a huge acceleration, which means its speed is going to change direction just like that. In a small amount of time, the speed of the bug can go from almost nothing because it just blew to, and now it's heading that way with a huge speed. That's a huge acceleration. That's what kills the bug. So it's Newton's second law that kills the bug. It's not Newton's third law, right? So if they're asking which of the things feels the greater force, they both feel the same force. Newton's third law. They've asked, which of the following describes this interaction between the windshield and not a bug, in this case, a rock? The car exerts a force on the rock, true, and the rock exerts a force on the car, true. The two forces are not equal in magnitude. They are equal and opposite, equal in magnitude, opposite in direction. The car exerts a force on the rock exerts a force on the car. The two forces are equal in magnitude. Check, D, and opposite direction. Number 10. And I think I'm going to stop after the number 10, which is this one, and then just record the second 10 in another video. Take a minute break before I continue forward. So let's just finish this one up. Number 10, two objects, X and Y, move toward one another and eventually collide with each other. Object X has a mass of 2m. So let's just sketch this up. Where's my drawing pad? There it is. So there's object X, which has a mass of 2m, and is moving with a speed of 2v naught to the right before colliding with object Y, which has a mass of only m, smaller or lighter in mass, I should say, less massive, and is moving with also half the speed, only v naught. So this guy has half the mass and half the speed, and they're going to collide. Which of the following describes the forces felt by both of them while they collide? Newton's third law. Newton's third law, right? It gives us the answer. They have to be equal amounts of force. We had to draw a free body diagram for them colliding. The moment of collision, boom, they're hitting each other in this moment. They want to draw a free body diagram. Well, this guy weighs more, so he has more normal force acting on him and gravitational force. This guy has, well, half as much because he's only half the mass. This guy feels a force. He's moving this one, bam, he smashes into him. Which way does he feel a force? To the right. Well, he's going to slow down, right? If he slows down as a result of running into it, and he's moving to the left, then the force must be to the right. So he feels a force to the right from guy A. Call it, no, X, from X. Which way does X feel a force? To the left. But how long would it be? This is where some students would draw a shorter one, saying, he feels more force because he's tiny. You feel the same amount of force. I didn't mean for this to go into this other one, but these would be equal. I couldn't really do it quite right, but these would be equal length. Oh, so sorry, I didn't mean to do that. This wouldn't be there at all. I'm just drawing in the wrong area. This guy right here that I tried drawing, made a mistake. Apologies. If this guy feels a force that's, I don't know, 1, 2, 3 units long to the right, then this guy feels a force that's to the left, also 3 units long. 1, 2, 3 units long to the left. These forces are equal. These are from the collision. This is the one he feels to the right as a result of colliding with him. This is the one that he feels to the left as a result of colliding with him. They'd be equal in magnitude, but opposite in direction. This would be force from y. So let's see. We just got to find one that says the forces are equal. The force exerted by x on y is F, and the force exerted by y on x is F. That sounds right. D. The force exerted on both of them is just F. The other one state that? It can't be. The force exerted by x on y is F to the right, and the force is, they have to be in opposite directions, right? One feels a force that's rightward, one feels a force that's leftward. Oops, I lost it. F to the right, F to the left. Why are these different? The force exerted by x on y is F to the right. Oh, I have to look more at the picture. My apologies. Yeah. Where's my picture? Gotta make sure that it's in agreement with this. So move this over. The force exerted on x is this guy. On y, so he feels y feels a force which way? To the right. That's correct. The force exerted by x onto y is a rightward force, which means C has to be the correct one because D looks similar, but it's claiming that y feels a leftward force. No, he feels a rightward force. While the force exerted by y onto x would be to the left. D. All right, I'm going to take a break there because, well, I need to take a break. Where I try to squeeze in another 10, the last 10. I'll just post them separately as 2 different links. All right, see you in a bit. Hopefully that was helpful.